Hello, my name is Patrick Kelly. I'm a master's student in the physics program, the physics master's program at Fresno State, and I'm taking chemistry 110A. And I'm going to give a very brief presentation on the paper I chose to present on. More extensive details and notes can be found in the notes I uploaded on Canvas if anyone wants to check those out. But I'm just going to give a very quick overview of the gist of this paper and why the authors wrote it. It's called Combining the Random Phase Approximation and Perturbation Theory for Theoretical Chemistry. That's the name of my presentation. So here's my outline. I'm just going to briefly talk about what the paper's about. I'm going to talk about some of the key concepts, namely the missing correlation energy, which is the main thing that the authors are trying to estimate. And I'm going to talk about the methods they used. They used the random phase approximation perturbation theory. And I'm going to talk about one of the sets of results that they obtained for the helium atom. And then I'll recapitulate at the end. So the authors of the name of the paper is RPA Natural Orbitals and their application to post-Hartree-Fock electronic structure methods. So they used orbitals obtained from what's called the random phase approximation, RPA, and they used them as a new basis set for quantum chemistry calculations. They combined these new basis functions with many-body perturbation theory, actually Moeller-Plosset perturbation theory, and they used them to calculate the electron-electron correlation energies for the helium atom and a number of other benchmark systems, including the hydrogen molecule and the fluorine molecule and diamond as well. So, as we know from class, Hartree-Fock calculates the correlation energy by assuming that every atom is subject to a field, which is the result of the average motion of all the other electrons. Because of this, Hartree-Fock neglects the contribution to the energy from the instantaneous electron configurations. And we can express the missing correlation energy with this expression 1, where E exact is the unknown exact energy of the true system. EHF is what Hartree-Fock estimates it to be, and then what's left over is the correlation energy, which is missing from Hartree-Fock. So the authors proposed a new basis of what they called natural orbitals from this RPA. There isn't enough time to discuss this in a 5 to 8 minute presentation, but I talk a little bit more about it in the notes on Canvas about what it is and its motivation. But the point is, it's one of probably many ways of getting a set of basis functions, and they used it to get what they called these natural orbitals, or that they used as a basis. Then they use this basis in many-body perturbation theory, Moeller-Plosset theory, to estimate the missing correlation energy. So as we went over in class and some of the notes, we briefly talked about many-body perturbation theory, and it turns out that you need to go to second order in many-body perturbation theory to get a contribution to the energy that's different from the Hartree-Fock contribution. So you end up with a term like this. So here is probably their most important result, at least for the helium atom. They're demonstrating that their method, or at least using the basis functions they used with MP2, they can get fairly rapid convergence. As the number of orbitals they keep adding on to the linear combination used gets larger and larger. we know it converges because basically after some number of orbitals, these red dots stop changing. And you can see they indicate that they're using this MP2 plus, they call them RPANOs in the paper, these natural orbitals that they're using. Also, they use this method to estimate the wave functions, which is they did here for the helium-2s orbital using their natural orbitals. It's the yellow line here, and they list some other methods too. Like you can see that Hartree-Fock, there's a significant disagreement with Hartree-Fock, which is this black line here. Here's their yellow. Excuse me, I'm saying yellow, I meant blue. They used this blue is their method using their orbitals. So this paper, it was an interesting synthesis of different physics and quantum chemistry concepts. That's why I chose it and thought it was interesting. And to estimate the electron-electron correlation energy for some commonly encountered benchmark systems. And one example that they did was the helium atom. If you're interested, more details can be found in the notes I will upload onto Canvas very soon. That's all. Thanks for listening. Bye.